All right. This is December 1st, 8 a.m. We're doing the final review all this week. Once again, lectures are reviews for 8 a.m. and 4 p.m. this afternoon. We're doing a tutorial final review Friday 1 to 3 in Brevard. Yes, everything will be recorded. Yes, everything will be posted, as if I would just delete it and then laugh maniacally. I'm trying to get the multiple choice versions done. They won't be covered in the video, but what I'm going to do is I'm going to work on them today and tomorrow and then get them posted on Blackboard, and then you can take a look at them. All right. Last time we were working, we did through problem 2. No, we did through problem 3. Are we on a different test? Oh, 4 p.m. Hold on. And I stand entirely corrected. This is the one. May 16th. Okay. Yeah, the appetizer was the thing. All right. This is, well, then let me stand corrected. Spring, and then if you're on Twitter and you're a fan of Ole Miss baseball, that should mean something. RF Hater version. Look them up. Okay. What we're gonna do. So we went through problem 3, correct? All right. So now it's just page 2. So on April 10th, J.B. Woodman crushes the ball off of Dominic Taccolini for a 2-run home run. This actually happened. Determine the initial velocity of the ball and the angle of the hit given the conditions listed below. So if we can get our initial conditions, L1, which is Y1, is 1 meter. L2, which is Y2, is 3 meters. The time of flight was 7 seconds. That eliminates this from being a quadratic equation. I need V naught and theta naught. The total horizontal distance between the launch point and landing point, which we will call X, is 120 meters. So those are the initial conditions and everything that we need to write down. It's a 2-dimensional motion problem, which means it's a 2-equation, 2 unknown. The 2 unknowns, velocity and theta. It's a 2-equation, or it's a 2-dimensional motion problem, which means you write x equals x naught plus v naught x t, and y equals y naught plus v naught y t plus 1/2 at squared. Why is there no a term for x?
It's only accelerating in the vertical.
It's only accelerating in the vertical, correct. Now, I would choose the origin. You could choose the origin really anywhere, but I'll choose it right at home plate at the base. That means x naught is 0. That means y final will be 3. That means y naught will be 1. Using the typical 2-dimensional launch, that's theta, that's v naught y, that's v naught x, that's v naught. V naught x is v naught cosine theta. V naught y is v naught sine theta. So filling those in for here, x equals V naught cosine theta t. Y equals y naught plus V naught sine theta t plus 1/2 at squared. In this case, gravity, or the acceleration, is negative g, so it's negative 10 meters per second squared, because gravity is pulling downward. Now let's identify what we know and don't know. What we do know, line goes under. What we don't know, line goes over. X, we do know. We don't know V naught. We don't know theta, but we do know t. Y and y naught we know. V naught and theta we don't know. We know t and a. So the two equations provide us with two unknowns. So we got to solve for it. How do we get rid of all this? Probably I would get rid of V naught first, find theta, and then go back. Because it's easier to solve for V naught than it is to pull that theta out. So x over t cosine theta is equal to V naught. Just solving for one of the variables that we don't know out of the equation. So the only unknown over here is t, and V naught is an unknown. Substitute y equals y naught plus, now the V naught comes into play, x over t cosine theta t plus 1/2 at squared. And what did I forget? Sine theta, yes. So right in here, there's a little sine theta. Now that t cancels with that t. I still have y and y naught. The x is still there. Sine over cosine gives me tan, and that's 1/2 at squared. Now I'm going to extract the theta. Y minus y naught minus 1/2 at squared is equal to x tan theta. Y minus y naught minus 1/2 at squared over x is tan theta, or theta is inverse tan y minus y naught minus 1/2 at squared over x. And that is your theta. So inverse tan, y final 3, y initial 1, minus 1/2 a negative 10 times 7, all divided by 120. And calculator, people. And wait, it's gotta be there. It's gotta be there. It's gotta be there. There it is. So it's 2 plus 5 times 49. Two plus 5 times divided by 120. So inverse tan of that gives me 64.1 degrees. Always use negative 10 in ballistics, because A is the acceleration, G is just the magnitude. So in this case, A is negative 10 or negative G. Theta is 64.1. V naught x over t cosine theta. X is 120. T is 7 cosine 64.1. 39 point what? All right, 39.2. That's good enough. And so that is a 2-equation, 2 unknown with 2-dimensional problem.
Could you use V equals V naught plus AT and solve for V naught that way? V would be 0 because it's being caught
It's been caught.
or been whatever.
No, it hit the ground. No. This is all about at launch point, it has a particular velocity. At the end point, it has another particular velocity. It hasn't hit the ground. It's the moment before. What you're suggesting is the snark answer. What is the velocity when it hit, or at the ground? 0, because it hit the ground, he. This is one continuous motion. You do not anticipate that something caught it at the end. It has those coordinates with a particular velocity, and that's it. Do not assume that it hit. That would affect the entire problem. It could be asked, well, what's the velocity at impact? Short, or should I say, the moment before impact, and then you would get Vy equals V naught y plus AT, and Vx is equal to V naught x. Vy is V naught y, or V naught sine theta plus AT. Vx is V naught cosine theta. V naught is 39.2. Sine of 64.1 minus 10 times 7. Back it up. And that gives us, oh, I didn't do it right. Minus 34.7 meters per second. Vx, 39.2 cosine 64.1. $17.12. So in component notation, the velocity vector at final is 17.1 x hat minus 34.7 y hat meters per second. And then you can continue and find it in polar notation, and that's just vector stuff. But it's not, the velocity at the end of a 2-dimensional motion problem such as this will never be 0. It's the moment before it becomes 0. I'd much rather have you make that mistake right now than on the final. Okay, number 5. Given the experiment shown, at what levels will the tube resonate? The velocity of sound is 350 meters per second. Your tuning fork is 280 hertz. So it is, because the tube will eventually have water looking like this. This is a tube, one opening, or what we would call a half tube. So this is exactly like what you would do in the lab. So the frequency for a half tube is F in V over 4L, where N is 1, 3, 5, etc. Probably at most there'll be like 2 or 3 resonances. So what I'm looking for is, as I told you in lab, it's easier to just kind of ballpark the distances. So L is V over 4F, 3V over 4F, 5V over 4F, and see what distances you get. 350, 4 times 280. .3125 meters. So the first one is roughly there. The next one, really all this is 3 times that F1. So times 3. 0.9375 meters. You could round it off, that's fine. And then, so that's L1, L3, L5. The fifth one, or actually those aren't F1s, those are L1s. 1.5625, which is greater than 1.1. So the two answers, the places at which it resonates, are at those two distances. And so this is what you would do in the lab. You would get your tuning fork, plug that in there, get a distance, multiply by 3, get your second distance, and then you pretty much know where those things should resonate. And I think that's number 5. Can't be greater than 1.1 because the tube itself is only 110 centimeters long. So if the resonating point is 1.56, the tube just can't resonate at it because it's not long enough. At those two. If I made the tube 150 centimeters, it still wouldn't resonate. If I said 160 centimeters, it would. In the lab, there were instances where tuning forks would only have 2 resonating places because the third resonating place would extend beyond the rubber stopper. There were other frequencies where there were 3 resonating places. Okay, number 6. All right, Rebel Rod and Reel Fish of Fury problem. Rebel Rod and Reel has 120 meters of fishing line on the spool. 120 meters. Spool has a radius of 4 centimeters. R, 4 centimeters. You cast out 12 meters of line. So really X naught is equal to 12 meters. It will run out at 120. The fish of fury takes the bait and begins to move away from you at 12 meters per second. So the velocity of the fish, 12 meters per second. If the fish's speed is constant, how long will it take before a spool runs out of line? Classic one-dimensional motion problem. X equals x naught plus v naught t. It doesn't accelerate, so there's no need for the 1/2 at squared. I'm looking for time. X minus x naught equals v naught t. X minus x naught over v naught is equal to t. X final, 120. X initial, 12. V initial, 12. So that's 108 over 12, 9. Yay.
What's that? 120 LT, what does that say?
The total length of string, which means that here's the rod, that's 12, so that's x naught. Once that hits 120, then you're out of string. So it started here, which means your x naught is 12. It ends up there, which means your x final is 120. All right, let's see. How many revolutions did the spool make when it runs out of line? So the length used is 120 minus 12, or 108. So during that motion, 12 meters was already out. It went another 108 meters. The circumference is 2 pi r. The number of revolutions is the length used divided by the circumference, or 108. Circumference is 2 pi r, so 2 pi r is 0.04. N is number of rotations, 429.7 rotations. If you ran 100 meters and each trip around the circle was 5 meters, how many times did you go around the circle? 100 divided by 5, or 20. So you just had to figure out the total length that was used, 108, divided by the circumference, 2 pi r. Remember that your r is in meters. And then you're good to go, 429. Go ahead. You wanted this? Okay. I really want, think about this. This is the thing that annoys me. I wish that they were blackboards, double blackboards that I could lift up, because up here, there's all this wide space, or space not needed. Or, give me a second screen, because then I could have a second Elmo, and then I could put the old paper over there. But no, they spent $500,000 on the room and about 25 cents on this gun. That's my rant for the day. Because if I had a second Elmo, I wouldn't get questions like that.
No, I agree with you. Like, schools need to update the fact that they still have chalkboards in it.
I know. But these chalkboards go side to side. That's zero help. In fact, They loved this so much when they expanded Coulter and put in new whiteboards. What do? They go from side to side. What's above those whiteboards? Nothing. Seems like a lot of wasted space. I got so mad. Plus, they do that weird thing where they rotated the seats by 45 degrees to make it look modern. Physicists did not design. How many left-handed desks are in there? How many? There are left-handed desks?
Yeah, because I get put at those for every test and I'm not left-handed.
Okay, fine. Welcome to my world. So, she understands. All the left-handers in the room understand. We don't show much sympathy. All right, are we done with the need for the second Elmo? Are you done? Thank you. All right. This is the kind of insolence I appreciate. Thank you. I need period, frequency, angular acceleration of the spool while the fish is pulling out the line. Which is the trivial one to answer? Which is the one that you could just say it's blah and this is why? Huh?
Angular acceleration.
Angular acceleration. What's the answer for angular acceleration? 0. Why? The velocity of the fish is constant. Hello? Heard a knock. If that is constant, omega is constant, and alpha, which is the change in omega with respect to time, is equal to 0. So that's the easiest one. The next one is you can answer either period or frequency. The period is the total time divided by the number of rotations. Total time 9, rotations 429.7. Nine divided by 429.7. So it is 21 milliseconds. I get 2.1 times 10 to the negative 2, or you can write 21 milliseconds. Or let's do it in seconds. 2.10 times 10 to the negative 2 seconds. Invert that to get frequency. Frequency is inverse period, 47.7 hertz. And so that is problem 6. And that is the RF Hader test from May of 16.
Dr. Eschenberg, I didn't see on any of the tests a static problem like you showed us earlier.
That's a static problem.
Right.
But we just went over a test with a static problem. Okay, so what's your question?
My question is, it was when you were talking to us about, right, it was we were calling it kind of like an MCAT problem, where we had an arm and we had something hanging off the arm.
Oh, that. Oh,
And,
I need to remember that.
You had told us that that was going to be on the final.
Thank you for reminding me. That may have been. I've been looking for problems.
So can you go over that today?
Oh, okay, we can go over that. I'm fine with that. We won't do anything like the the mass isn't going to be sitting in water because that's just freakish. but I can do this. Massless arm, unknown mass that's hanging. Why are we all mad at him now? Should I give out his name so you can just beat him up after class? Just email. Okay, I'll email it to you guys. Y is 1.2. This x1, which is this distance, is 1 meter. This distance, which we will call x2, is 1.5 meters. The mass of the string, so this is string, this is a massless bar, that's just the wall. The mass of the string is 10 grams or 0.01 kilograms. This is such a good problem. You flick at the string resonates at 800 hertz, and it's its second harmonic. What's the hanging mass of the string? Or what's the hanging mass at the end of the bar? So this is a classic hybrid problem. If I was truly mean, I would put it in water and then, but that's a good homework problem. For a test, people would go out of their minds. It's a two-part problem. There's the tension in the Y. There is the tension in X. There is the hanging mass times gravity down. This is the rotation point. So in a way, we've got this weird torque problem going on. It's also a sound problem. You know that for string, NV over 2L, V is the tension in the string divided by linear mass density, and linear mass density is the mass of the string divided by the length, which we will call the hypotenuse. So substitute. Frequency is N over 2 hypotenuse. V is tension over lambda. N over 2 hypotenuse, because the vibrating length is the hypotenuse itself. Tension over mass of the string. The hypotenuse is in the denominator, and since lambda is in the denominator, the hypotenuse goes up here. Extract tension, frequency squared, N squared over 4H squared, tension H over MS. H's cancel one of them. Solve for tension, 4HF squared MS over N squared is equal to tension. Now, the hypotenuse is the square root of 1.2 squared plus 1. So 1 squared. So probably now would be a good time to just get that number. And I would carry it out to a little bit more sig figs than normal. 1.562 meters. So this is 4 times 1.562, frequency 800, mass of the string 0.01. N is 2. Ooh, it's almost like I'm planning ahead. Those cancel. And so the tension in the string itself, ooh, and I got an exact answer still in the calculator, times 800 squared times 0.01. Oh, this is really good. 10,000 newtons. Because it's actually, if you can see it, 9997.11. So we'll just round it to 10,000 newtons. So that's the tension in the string. Yes.
Where's the height?
That's hypotenuse. Hypotenuse, which is y squared plus x squared square root. So the first thing really that you had to do with this problem was find the tension in the string. Let's see, is this still going? Yeah. Now that you know this, you can find, or you can get this angle after everything is said and done. So theta is inverse tan of y over x1, which is inverse tan of 1.2 over 1. Or inverse tan of 1.2. 50.19 degrees. Okay. Because that's theta, and you know the relationship of sine theta is ty over t. So t sine theta is equal to ty. So this becomes 10 to the fourth sine 50.19 is equal to ty. And I get 7682 newtons. And that is t to the y. So the first real problem, and this is the reason why hybrid problems are a little bit interesting, or as the MCATs call them, passage problems. They give you multiple problems in a row. They're all interrelated. For this, you identify that you have all the information except for tension. Solve for tension. Now that you've got tension, find Ty. We got Ty because you've got the angle. You can get the angle fairly quickly. The last part is a torque problem. Because this bar is not rotating, sum of the torques is equal to 0. That force does not affect anything because it's pointed right at the rotation point. Ty is perpendicular, MHG is perpendicular. So the two torques are Ty times its distance, x1, MHG times its distance, x1 plus x2. Now really, they're going to be opposite sides. To the right, up, out of the page, positive. To the right, down, into the page, negative. And now all you got to do is solve for MH. MHG, x1 plus x2, ty, x1. MH TY X1 over G X1 plus X2. TY 7682 X1 1 G10 X1 plus X2 2.5. So 7682 divided by 25. And I get 307.3 kilograms. Answer. So it's a combination of, if I broke this up into three little problems, if I said, and actually there would be three appetizer problems. Given an arrangement of a string with that frequency and harmonic, that mass, this length, give me the tension. You could do that. If I said, given that tension and that angle, give me Ty, you can do that. Given that Ty and that MHG, solve for MH, you could do that as well. What this is three appetizer problems slung together. Little bit of duct tape put together, and what you've got here is a very nice hybrid problem. Have I really decided to put this on the test? I haven't decided. I haven't even written the test. But a problem like this is legit. If you're ready for this, if you go backwards and forwards in this, add vectors, do that 2D motion thing, I mean, you've pretty much got the test up to at least a 70%. I mean, if you answer partial credit on the multiple choice, or if you do really well on the partial credit on the problems, multiple choice really well, I mean, you could trip over a 60 with no problem. 60%. It's not going to be that tough. It'll be tougher to hit 80%, 90%, 95%. This is the one test where I'm like, I plan on curving. So at least I can put in some problems that'll test you guys. Because overall, the averages for tests 1, 2, and 3 have been fair, if not a little bit high. The afternoon class, they're going to get what's coming to them. So, you guys, I like you guys. It'll be fun. Afternoon people don't like so much. Shh. And you'll know what I say in the afternoon. Those people in the morning can't be trusted, so I'm gonna nail them to the wall. So you go to both sides, yeah. So, all right. We've still got quite a bit of time. We've done the May 16. I've also posted really what I'm going to do is I'm going to do the multiple choice for all three versions of the final that I have, or all three dates of the final. There's a summer, let's look at the summer one. This is the summer final from from a year and a half ago. This problem we've gone over, that problem we've gone over, this problem we've gone over, but we only did energy, we did not do motion. So let's do motion on this. This is Sigma version, summer 15, problem 1. And I believe what went in the box was the final velocity. Because I mean, I really just gave you everything except that thing. So write down what goes on. Draw a little sketch. The initial velocity is 0. That means energy initial minus energy removed through friction, energy final, energy initial, it will just be M2GL. Oh, I'm sorry, correct. Can't do it that way. All right, draw the picture. Okay, what this requires is you've got to sum the forces on each of the masses. Let's do the hard one first. You draw the force diagram. Tension, friction, boo, friction. You've got mg down, you've got normal force up. Because it's moving to the right, friction force is to the left. Sum of the forces vertically is equal to 0, which is normal force minus mg. Will I add a third force to affect this? I don't know. I haven't decided yet. But in this case, there are only this many forces. Fn is equal to mg. Friction force is equal to mu sub k, normal force, which is mu sub k, mg. Now we sum the forces in the horizontal. Sum the forces in the horizontal. Because of the bendy number line, left is negative, right is positive, just as up is negative and down is positive. Sum of the forces in x, positive T minus friction force. This will all equal M1A. A is not differentiated between A and A1, A2 because the acceleration of both objects are identical. I'm going to solve for tension. Tension equals M1A plus friction force. This is M1A plus mu sub k M1G. And that is equal to the tension. Now really, this type of problem is a 2-equation, 2 unknown. However, I so often just don't worry about tension. It's best just to solve for tension in both equations, put them together, and bam, you can get A. Now the loopy-droopy number line demands that up is negative and down is positive. There is a downward force of M2G and an upward force of tension. Just like acceleration, the tensions aren't differentiated because they're the same as well. Sum of the forces in the line of motion, which is equal to M2A, is equal to minus T plus M2G, or T is equal to M2G minus M2A. So we have two expressions for tension. We're going to put them together. M2G minus M2A equals M1A plus mu sub k M1G. Now I get to solve for A. M2G minus mu sub k M1G is equal to M1A plus M2A. Factor out G's and A's. G M2 minus mu sub k M1 and then A, M1 plus M2. So G, M2 minus mu sub K M1 divided by M1 plus M2 is equal to A. Now probably is a good time to get the get a number. 10 M2 is given, 20 minus mu sub K 0.2, M1 is 12. M1 12 plus 20 what? 5.5? Hold on. Times 10 divided by 32. 5.5. Exact. So that's the acceleration. Now, couple things about this. The way that the number line is set up, down is positive. We got a positive answer as our acceleration. Of course this thing should go positive. M2 is bigger than M1. M2 is suspended, so M2 should fall. M1 should go to the right. A should be positive. If I got an acceleration of 15, could that be an acceptable answer, the way that this problem's set up? No. It could never be greater than 10. So for a problem like this, it could never be negative, it could never be greater than 10, because unless there's an external force pushing down on that object, the maximum acceleration it could have is 10. Now it's a one-dimensional motion problem. 0, 6, V naught is 0, A is 5.5. May have asked also for the time of fall. Let's do both. One-dimensional problem. X equals x naught plus phi naught t plus 1/2 at squared. And v equals v naught plus at. V naughts are 0, starts at rest. Start at the origin. X naught is 0. I know final x, a, but not t. I don't know final v, but I do know a. That's the equation that I attack. Find t. 2x over a is t squared. Square root of 2x over a is equal to t. 2 times 6 divided by 5.5 will give me the time. 12 divided by 5.5. Square root of this, 1.48 seconds. Final velocity, 5.5 times 1.48 gives me a final velocity of 8.12 meters per second. Yeah. Well, I mean, if you've got T, you might as well just knock out final V while you're at it. Or if I ask for final V, you're going to get T along the way. So any more questions on this? So we've done it in this class on Tuesday and Thursday, Atwood's machine with energy, Atwood's machine with motion. You're going to get one of the two. Problem 2, we've done on Tuesday. Problem 3, you've done something like this on test 3. Over the weekend while I'm writing the test, I should be getting the solution sets for all the problems, or all the tests, so that you can take a look at them. We've just done this. This is a torque bar problem. This is easy. And then this is conservation of angular momentum. And this could be a good problem in the sense that when I say alpha is equaling 0, what I really mean is no external forces. So a potential problem that you could get is that the angular momentum is conserved, or something like the Fisher Fury. I'm not sure which one, but I will say as a bit of advice is there will be a moment of inertia problem, part of a rotation problem, or maybe just simply an appetizer problem, where you'll have to calculate the moment of inertia, and you will have to use the parallel axis theorem. I mean, it is coming. I would say it is as certain as adding vectors. Yes?
Work number 6?
Okay, we can work number 6. Since we still have 15 minutes. All right, in number 6, something is rotating at a frequency of 4 hertz. It changes its geometry, and then I ask, how long does it take for it to rotate using its new geometry? So the big question is, you got to get the moment of inertia for each of these correct. The initial moment of inertia is the moment of inertia of the disk plus 3 times the moment of inertia of those points. The moment of inertia, and all these will be given in terms of the base moments of inertia. And in this case, parallel axis theorem is not being used, but this is still a good exercise. Moment of inertia of a disk, 1/2 mass of the disk, r squared, 3 times moment of inertia of a particle, mass of the particle, radius of the disk squared. Because they're all at the edge. So this becomes 1/2 70 r6 squared plus 3 mass of the particle, 1/9 mass of the disk. So 70 divided by 9, r squared, 6 squared. So this gives me 35 times 36 plus 70 divided by 3 times 36. 2,100. Kilograms meters squared. Now the moment of inertia after is still the moment of inertia of the disk plus 3 times the new moment of inertia of the point particle. So this is 1/2 mass of the disk, r squared, plus 3 times mass of the point, r prime squared, or really actually how I used it in the test, little r squared. So this is 1/2 70 6 squared plus 3 70 divided by 9 Little r is big R divided by 2, so this is 3 squared. 3 squared divided by 9, that goes away. So this is 35 times 36, same as before, plus 210. 1470 kilograms meters squared. So those are the new moments of inertia. So the moment of inertia went from 2100 down to 1470. Now, a couple of questions are asked. Give me L initial over L final. What should that number be? That's a trivial answer. Should be 1. Conservation of angular momentum demands that the angular momentum never changes. So those are the same, and it should be 1. I initial over I final, well, we've got the numbers, 2100 divided by 1470, and so you can calculate that out and get whatever you need. Now, the thing that I really need is the period, the new period. L initial equals L final. I omega is equal to I prime omega prime. I omega over I prime is equal to omega prime. Now 2 pi f is equal to omega. So this becomes I 2 pi f over I prime is equal to 2 pi f prime. The 2 pi's cancel. So I f over I prime is equal to f prime. And then you just take the inverse of this. I is 2100. We're going to still need that number. 1470. Frequency new is 4. So the new frequency is 5.71. The new period is 1 over the old frequency, and so that new period is 0.175 seconds. So it takes 0.175 seconds for this thing to rotate. I want to know how long does it take to rotate 10 times. Total time is the number of rotations times the new period. So 1.75 seconds. Because 0.175 times 10 is 1 3/4 seconds. So some of the numbers get a little bit weird, but the number at the end ends up being quite nice. And so that is number 6 for sigma of the summer of 15 final.
Why'd you multiply by 10 though?
Because I wanted to know how long would it take to rotate 10 times. Because I knew that it would take 0.175 seconds to rotate once, multiply by 10 to get the number of rotations, or the amount of time for 10 rotations.
Two different ways of running, how to find time, or wait,
Say again?
where you went from the capital T prime to the T equals T.
Total time divided by number of rotations is period. So I could have written probably what I should have written before is the total time divided by the number of rotations is the period. And then I changed it to that, and I get this.
What's the number for rotation?
Numbers of rotations was 10. It was provided for in the test. All right. That's it for Physics 213. If you want a little bit more, tomorrow at the tutorial final review from 1 to 3 in Bishop's main lecture hall. If there are little kids in there, kick them out. It's our space. Have a good day.